Hey math fans, Alex here. Last time we talked about something called generating functions, and more specifically generating functions of a random variable x. Namely, this random variable is discrete, so I should probably add that in there. But the idea is that if you have a discrete random variable x with PDF given by px of k, then the generating function is defined to be this. It's the infinite sum from k equals 0 to infinity of the probability density function times z to the k. Also, last time we derived a couple of useful properties. In this video, we're namely going to be using the first two for expected value and variance, and I'm going to show you how we can use those to more easily find these quantifiers of a probability distribution. Okay, so let's go ahead and get started with the binomial distribution. And we should know what the mean and variance of the binomial distribution is, but let's derive it a different way. Okay, so the generating function is going to look like this. So it's going to be the infinite sum from k equals 0 to infinity of the PDF times z to the k. Okay, but the PDF of a binomial distribution, if you'll recall, we had those binomial coefficients, right? So it's going to be assume little n trials, and then it's going to be n choose k, p to the k, and then q to the n minus k. So this was the PDF for a binomial variable. And then we also have to take that times z to the k. That's important because now we have two terms that are both being raised to the k, so we can combine those. So this is going to be the infinite sum from k equals 0 to infinity of the binomial coefficient times pz to the k times q to the n minus k. And then what we have is a situation where we have the binomial coefficient n choose k, something to the k, something else to the n minus k, and by definition of the binomial theorem, that is going to be the first something plus the second something to the n power. You might be a little skeptical of this infinity, but remember the binomial coefficient, we defined it to only be non-zero up to k. So really I can go ahead and erase this, and we're only up to n. So k goes from 0 to n, right? Because if we have something like n choose n plus 1, we can't choose more than we have. So we're defining that to be 0. Okay, and then this, I should specify, is from the binomial theorem. Okay, now, this is fine. This is a good generating function for the binomial distribution. Sometimes you can call it probability generating function if you want, but to find the expected value then, okay, so since ax of c, we found that to be pz plus q to the n, we know that the expected value is just simply the first derivative evaluated at 1. Okay, so the first derivative of this is technically a polynomial, right? And polynomials, I mentioned, are analytic, which means in the complex derivative world, you should be able to differentiate using the power rule, no problem. If complex analysis is not your forte, then just differentiate this good old Calc 1 style. So bring the n down, take it times the inside, raised to the n minus 1, and then the chain rule says that you do have to differentiate the inside. Okay, but all of this, the derivative, it's linear. The derivative of that is just the coefficient of z, which is p. Okay, so the derivative of the inside is just p. So that's what we get evaluated at z equals 1. Okay, but if I plug in z equals 1, I'm going to go ahead and pull this p out in front. So it's going to be np times p times 1 plus q to the n minus 1, which is just p plus q. Okay, but p plus q, the probability of success plus the probability of failure, has to be 1. So we have np times 1, which is np, which matches what we knew the expected value to be. Okay. Now, to find the variance, we're going to have to take the second derivative of this. Okay, so we're going to have to take the second derivative evaluated at 1. So we're just going to take this and differentiate it again. So I'm going to, again, pull the NP out. Then we're going to use the product rule again on this. We're going to bring the n minus 1 down. So this is times n minus 1 times pz plus q to the n minus 2 times the derivative of the inside again, which is p, evaluated at z equals 1. So evaluating it at z equals 1 means that this term is going to be 1. Okay, so I'm not really going to write that again, but we're going to have n times n minus 1 times p, so that's a p squared. Okay, or n squared p squared minus np squared. There's a reason I distributed that. So then the variance is, let's see, that's going to be ax double prime of 1 plus ax prime of 1 minus ax prime of 1 squared, which if we plug everything in, we get that this is equal to, we should do this, so this is going to be n squared p squared minus np squared plus np minus np squared. Okay. Well, n squared p squared and np quantity squared are the same thing, so those are going to cancel. And then after factoring out an np, we're going to get that this is 1 minus p, but 1 minus p is just q. So the variance of the binomial distribution we got to be npq, which matches exactly what we knew the variance to be. All right. Next example, let's go ahead and find the mean and the variance of the Poisson distribution. So the Poisson distribution, if you'll recall, so again, I'm just going to go ahead and write out the definition. So it's going to be the sum from k equals 0 to infinity of the probability times z to the k. Okay. But then, remember the PDF, oops, don't know why I did that, but the PDF of the Poisson random variable is equal to let's see, that's going to be lambda to the k over k factorial times e to the minus lambda, where lambda is just some parameter. Okay, so then that's going to be times z to the k. All right, now we can pull the e to the minus lambda out because that has nothing to do with k. So I'm just going to go ahead and pull out that e to the minus lambda. And then we have this infinite sum from k equals 0 to infinity of, and then same thing as before, we have two things being raised to the k power. So I'm going to go ahead and combine those. So it's going to be lambda z to the k divided by k factorial. And then that is going to be the definition. That is going to be the definition of, it's going to be the definition of e to this thing, to the lambda z. Okay, and then we can clean that up a little bit. These are being added then due to the power rule for exponents. So then that's going to be, let's go ahead and factor out the lambda, and then we have z minus 1. Okay, so that's the generating function for the Poisson distribution. Let's see if that checks out. The expected value should just be the first derivative evaluated at 1. So let's take the derivative of this. E to some power, that's going to go ahead and be analytic. And then since lambda times z minus 1 is also analytic, the composition of those functions are going to be analytic. Okay, which means we can differentiate this without a problem. So we're going to pick up a lambda from the chain rule times e to the lambda z minus 1, evaluated at z equals 1. Well, plugging in z equals 1, this is 0. E to the 0 is 1. So we just get lambda times 1, which is lambda. Now let's go ahead and differentiate this again. So differentiating this again, we have that ax double prime of 1. Well, let me leave that to you as an exercise to do, actually. So, exercise show that the variance of x is also lambda. And again, just follow the same exact procedure. It's not too bad. Okay? So now I want to talk about a brand new kind of distribution. And in order to talk about that distribution, maybe let's motivate it with an example. Okay, so suppose that I have a string of random digits from 0 to 9. And maybe I really want a 0. So after some 0, I maybe want to know the probability of getting, say, at least 3 other digits, probability of getting at least 3 other digits before another 0. Okay, so blah, 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 eventually we get a 0, and then I need at least 3 other digits before I get my next 0. What's the probability of that occurring? Okay? So in this case, we can just kind of model this as a random variable. Okay, so what we have is that x is going to represent the number of non-zero digits before getting a 0. Okay? Another way of phrasing this, because we want a 0 ultimately, like that's what we're talking about here, the number of non-zero digits can also be phrased as the number of failures. Okay, but we can just stick with the number of non-zero digits for now. And we want the probability of getting at least 3 other digits before another 0. So we have that the random variable x is going to be greater than 3. Okay, well, just based on simple probability rules, it's going to be a lot easier because x, theoretically, could go to infinity. I could have a trillion non-zero digits before getting a 0. Right? The Borel-Cantelli lemma kind of says that that's going to have a finite probability. I mean, it could happen. So the probability that x is bigger than 3 is going to be 1 minus the probability that x is going to be less than or equal to 3. Okay, and the probability that x is less than or equal to 3 is going to be the probability that x could be 0, x could be 1, x could be 2, or x could be 3. You just have to find those probabilities. But those probabilities aren't that bad, actually. So let's go ahead and do that. So what is the probability that x is equal to 0? Well, that means that we don't have any more non-zero digits, and the next digit is a 0. What's the probability of that occurring? Well, since these are all random and there are 10 digits, that's just going to be 1/10, which is also, we can label that little p, probability of success. Okay. What's the probability that x is equal to 1? Well, the probability that x is equal to 1, that means that you have a 0, the next digit cannot be a 0, so not a 0, and then we have a 0. Okay, so two things have to happen. The first digit can't be a 0, which occurs with probability 9/10, and this is independent because they're all random, so that means we multiply the probabilities with and the second digit has to be a 0. So that's times 1/10. Or in other words, this is actually just the same thing as Q times P, where Q is the probability of failure. Okay, hopefully you're starting to sense a pattern, because the probability that x is equal to 2 means that you have 2 non-zero digits. That's going to be 9/10 times 9/10 times, and then the third one has to be a 0. If this wasn't a 0, that means that it would have to be a non-zero digit, which we can't have. So this is also the same as q squared times p. And the probability that x is equal to 3, that's going to be, well, we have 3 non-zero digits before getting a 0, which is q to the third power p. Okay, so ultimately to find this probability, we just have to add all those up. Okay, so probability that that x is greater than 3 is going to be 1 minus probability that x is equal to 0 plus the probability that x is equal to 1, and then we have plus the probability that x is equal to 2, I might as well just square that, plus the probability that x is equal to 3. And as much fun as it is to type this into a calculator, I'm going to go ahead and show you the online calculator on StatTrek for it, so just give me a second. Okay, so StatTrek actually didn't have a geometric distribution, so I found this one. Credit goes to Matt Bognar from the University of Iowa. So what's the probability of success? The probability of success was 0.1, but we wanted there to be at least 3 non-zero digits before a 0. Okay, so they only have greater than or equal to, so that's x is greater than or equal to, say, 4. And we get our answer of 0.6561, which is exactly what you would get if you type that in your calculator. So we get 0.6561. Okay, and that's essentially the geometric distribution. We're going to kind of define it formally, of course, and then talk about the generating function, but there you have it. Okay, so the idea is we're going to go ahead and let xi be Bernoulli with parameter p. And this time, we're going to define the random variable x as the number of failures before the first success. So it's essentially a number of trials, not the total number of trials, because that could be infinite, but just a number of trials. Okay. Then what we have is that the probability distribution is going to look like this. So if we want k failures before the first success, that means that that's a failure, that's a failure, that's a failure, and we have k of them. So we have k failures. But then in order to stop the failure train, this has to be a success. Okay, so this is a failure with probability q, which means all of them are q since these are independent and identically distributed, which means that this last one has to be p. Okay, so this is going to be q to the k power times p, or sometimes you might see it as 1 minus p to the k times p, or some kind of variant of that. Okay, I might just stick with this one for today. The other thing that I want to mention before you get mad at me, occasionally this is defined not as the number of failures before the first success, but the number of trials before the first success. Okay, so in this example, we could have defined this variable as the probability that the number of trials before the first success was 4. That means a success occurred on the 4th trial, at least. Okay, which is kind of the same thing here. And I'll have you do an exercise kind of relating these two definitions, but right now let's just stick with number of failures. Okay, so I just want to make a comment here. This is very, very similar, and the reason that I wrote that xi was Bernoulli, this is very similar to the binomial distribution, okay? However, the binomial distribution had this binomial coefficient because there are multiple ways that things could happen, right? You had number of successes where those 2 successes could have occurred anywhere in the fixed number of trials. Well, now there's only one way this could possibly happen, so you can kind of think of this a little bit as Bernoulli with the binomial coefficient always equal to 1. Okay, so let's go ahead and start on the generating function. So since we have that the PDF was QKP, we can do this in the same way. So the generating function, which was defined as this, of x of k times c to the k, where the PDF, I'm just going to go and plug that in, that is q to the k times p. And oh, look, we have 2 things. Just like in the previous 2 examples, we have 2 things being raised to the k power. So we can go ahead and combine those. So this is going to be qz to the k times p. First thing that I'm going to do is I'm going to go ahead and pull the p out. I'm going to pull the p out. And the second thing that I'm going to do is I'm going to realize that in order for this to work, I need the magnitude of z to be less than or equal to 1. And then if the magnitude of z is less than or equal to 1, Q is the probability of failure, which is 1 minus the probability of success, and that's almost never equal to 1. Okay? It's almost never going to be equal to 1. And even if it was equal to 1, well then QZ is just Z, and then as long as Z is strictly less than 1, then this still works. So I guess what I'm trying to say is we also have to assume that Q is not equal to 1. In other words, we're assuming the probability of success is not 100%, because otherwise this sum will diverge. Okay? So in that case, then we're good. because since this we can say is now strictly less than 1 in magnitude, now we have a geometric series. Geometric distribution, geometric series. Yeah, that's where it comes from. Okay, so this is going to be, let's see, it's going to be P times 1 over 1 minus QZ, which we're going to go and write as P divided by 1 minus QZ. That is the generating function. Okay, now to find the expected value and the derivatives, derivatives aren't the funnest because, well, it's a rational function, but that's life sometimes. So you can find the expected value using the definition, but it's actually not very straightforward this time, okay? Because when you just try to do this, this is going to be from, say, k equals 0 to infinity of k times the probability density function, which is q to the k times p. This is not a geometric series. Okay, so you're going to have to come up with a trick, and it's not a hard trick once you see it, but the whole point of generating functions is to bypass that entirely, right? And just mindlessly take derivatives. So this is going to be ax prime evaluated at 1. So we have to differentiate this. So we can just use the quotient rule if you want. So we're going to take the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function. The derivative of the bottom function, since it's linear, is just the coefficient, which is negative q, all divided by bottom squared. Or as I like to say, low d high minus high d low, square the bottom, and away we go. Credit goes to Professor Leonard for that. Okay, so this is 0, and this is PQ divided by, and we still have to evaluate this at z equals 1. So this is going to be PQ divided by 1 minus QZ squared, evaluated at z equals 1. But when we plug in z equals 1, we get PQ over 1 minus Q squared, right? Q times 1 is Q. 1 minus Q, though, is P, so this is really PQ over P squared, which gets us Q divided by P for the expected value. Okay? So the variance, probably going to also have you do that as an exercise. The variance just involves taking the second derivative and evaluating at 0, but you can go ahead and show that the variance of this distribution is going to be Q divided by P squared. Okay, now, sorry for making you do all these exercises, but I genuinely think that they're pretty useful and important. I'm going to have you do a couple of other exercises involving the geometric distribution just to kind of close it out. And I think in the next video, we're going to revisit an example that we did earlier. Okay, so let me just write these exercises and walk you through them, and then we'll call it a day for this episode. Okay, so here's some additional exercises over the geometric distribution, which, by the way, just has parameter p. Okay, so the first one was an exercise that was actually from chapter 4. It's exercise number 12, so if you want to look at that document, it should be in the chapter 4 review video along with the answers. And this is a geometric distribution, and it's actually the one that we talked about. So you should be able to do that to easily find the mean and the variance. Okay, and here's kind of the second exercise. So sometimes we can define the geometric distribution a different way. So let y be geometric, where this time y represents the number of trials needed before a success. Okay, so for example, if I really want a 0, basically we're counting the number of trials that I need before I get a success. Okay. So part A, go ahead and show that the probability distribution function for that looks like this, q to the k minus 1 times p. Okay, maybe draw those blanks just as a hint. And then part B, show that the generating function with this PDF, even if you aren't able to get the PDF, you can just use it to show that the generating function looks like that, and then use this generating function to get this for the expected value of y and this for the variance of y. So jury's kind of out on which one to use. You should really know both and kind of how x and y are related. But that's kind of a little bit on the geometric distribution, as well as applying or starting to apply the generating functions. In the next video, we're going to continue to apply the generating functions to a problem that was very, very difficult to figure out that I assigned as an exercise. So we're going to go through that. Hope to see you there and have a great rest of your day.